A breadcrumb demonstration. Data-intensive computing systems, such as Apache Spark and Flink, enable scalable processing of queries over nested data stored in a wide variety of data formats. These systems allow users to express their queries in a high-level declarative language that abstracts away details like distributed execution. However, they lack comprehensive support for query debugging. BreadCrumb addresses this shortcoming. It extends Spark's DataFrame API to compute query-based explanations for missing answers. Given a why not question, which describes the missing query result that the user expected to be returned, BreadCrumb determines sets of operators in the query that prevent the result of interest from being returned. Our approach extends existing solutions for missing answers in three critical aspects. A, it supports nested data. B, it can identify errors where the user has selected an incorrect attribute by leveraging schema alternatives. C, it scales to hundreds of gigabytes in the input data. As displayed, BreadCrumb runs in a Jupyter notebook with an Apache Torrey kernel. This allows data engineers to share debugging sessions. To familiarize attendees with BreadCrumb, we illustrate an end-to-end debugging session using a toy Twitter dataset and query. The toy example consists of 3 tweets represented by the user tweeting it. The tweet may reference retweeted or quoted tweets that were mentioned in the tweet. Note that the retweet and the quoted tweet are nested elements that have the same structure. Further note that 2 nested tweets hold the name J, one in retweets, the other one in the quoted tweets. Consider the following program that computes the list of texts retweeted more than 10 times with the user mentioned in the retweeted tweet. This program first flattens out the retweeted tuple in the projection. Next, it filters the retweets by their retweet count before it flattens out the nested relation of mentioned users you mention. Finally, the query projects onto the retweeted text and the mentioned user's name. The query result contains 2 tuples with the names Ava and Tom. However, it lacks an entry for J, which we were expecting. We use BreadCrumb to understand why J is absent from the result and which query operators need to be modified to make J appear in the result. In BreadCrumb, why not questions are specified as tree patterns, enabling the user to address arbitrary nested elements. Our example question is encoded in the displayed tree pattern. Its root node represents top-level tuples in the result. The text and name nodes represent the tuple's attributes. As shown, the name has to match J. The quotation mark in the text node is a placeholder matching any value, so any text is fine. Next, we use BreadCrumb to generate explanations without considering changes to the attributes referenced in the query. We have one alternative and obtain one explanation. BreadCrumb displays the query tree to highlight the explanations in orange. In the shown tree, the marked filter is the reason for J's absence from the result. Now we know that we can modify the filter operation to make J appear in the result. While the explanation is credible, other reasonable explanations are missed, unless we also consider incorrect attribute choices as sources of errors. We now rerun BreadCrumb, this time taking schema alternatives into account. Currently, schema alternatives are provided as input by the user, but we could also leverage existing schema matching techniques. In this example, the quoted attribute is considered an alternative for the retweeted attribute. When computing the explanations, BreadCrumb evaluates both schema alternatives simultaneously, using the retweeted and quoted attributes throughout the query. In addition to the explanation produced without schema alternatives, a second explanation is returned. As shown, it identifies the first projection, because replacing the retweeted with a quoted attribute in this projection yields J in the query result. We have successfully tested BreadCrumb's scalability on hundreds of gigabytes of Twitter data, DBLP data, and TPCH data. Attendees of the demonstration are invited to formulate their own queries and why not questions over the mentioned datasets.